I welcome you guys back to Fees Unveil. My name still remains Franklyn Einstein. So we'll be continuing from where we stopped in the last video. We did problem solving on electric field part 1. Now this is problem solving on electric field part 2. Alright, so we're going to be solving more questions now from where we stopped in the last video, and I hope you learned everything in the last video. Remember, if you have questions, please put it on the comment section and I'll be there to reply you. Alright, you understand? So now moving on to another question. Let's start in solving more questions on dipole moments. Work done. Let's solve questions on axis, alright, where we apply the vectorial part of the electric field and so on. So let's move on to the first question. So the question says, what maximum torque does an external field of 10 to the power of 5 Newton per coulomb exert on an electric dipole, each with a charge of 10 to the power of negative 6 coulomb and separated by a distance of 2 centimeters? So that's the first question. Now the second question is, how much energy would be required to rotate the molecule 45 degrees from its equilibrium position of minimum potential energy? These questions are very simple. Well, kind of very long. Solve this question. It's very simple. So the first step is solution. But this question is long though. What's maximum torque? You can do it. What's maximum torque? So our max is what we are asking for. This formula for maximum torque is in the other video. You can go ahead and go and watch the other video. That is the problem solving on electric field part 1. So formula you need for all the questions we're going to solve today are there. So the maximum torque is equal to the electric dipole moment times the electric field, right? And that's what we are asked to find. Do you understand? You understand? All right. So an external field of 10 to the power of 5 Newton per coulomb. External field of 10 to the power of 5 Newton per coulomb. Newton per coulomb is unit of what? Electric field. So electric field is equal to 10 to the power of 5 Newton per coulomb, or you can write it as 1 times 10 to the power of 5 Newton per coulomb. Anyone and you're still okay. Alright? So now they say it exerts on electric dipole each with a charge of 10 to the power of negative 6 coulomb. Remember I said dipole contains two charges separated by what's a distance. Alright, so those two charges are of equal magnitude. You just pick one of the charge, and Q is equals to what? 10 to the power of negative 6 coulomb, or you can write it as 1 times 10 to the power of negative 6 coulomb. They are all the same thing, and coulomb is unit for what? Charge. Alright, separated by a distance of 2 centimeters. Now distance A or L equals what? 2 centimeters. But centimeter is not the unit of what? Distance. So you convert centimeter to meter. And how do that? You divide by 100. Good. So 2 divided by 100 is what? 0.02. 0.02 meters. Very simple. Alright? So now, can we still go ahead in finding maximum torque? We don't still have our electric dipole moment, right? Now what's electric dipole moment? Electric dipole moment, P is equal to twice the distance of separation times the charge, right? That is equal to 2 times what's the distance of separation? 0.02. Okay, what's the charge? The charge is 1 times 10 to the power of negative 6. And when you multiply everything, you get what? You get 4 times 10 to the power what? Negative what? 8. And what is the unit for electric dipole moment? Coulomb meter. Of course, charge is in coulomb, distance is in meter. Coulomb meter, not meter coulomb. It looks more beautiful as coulomb meter. Now let's go ahead in imputing this into this. So our maximum torque, our max, is equals to this times this, right? Electric dipole moment times electric field. So for dipole moment is this 4 times 10 to the power of negative 8 times our electric field is what? 1 times 10 to the power of what? 5. And that's what? 4 times 10 to the power of what? Negative 3 watts Newton meter. Newton meter is unit for what? Torque. And this is all for the first part. Now moving on to the second part. How much energy? Energy, work done. They're the same thing, alright? So energy, let me write in this place, please. So energy for the second part is the maximum torque multiplied by the cosine of the angle at equilibrium minus the cosine of the angle rotated. Now the angle at equilibrium is 0 degrees, while the angle rotated will be given in the question, and our question is what? 45 degrees. So this is energy or work done is equals to tau max multiplied by cos. The angle at equilibrium is what? 0. Now the angle rotated is what? Cos what? 45 degrees. Get that? So that is work done or energy is tau max. What is cos 0? Now cos 0 is 1 from trigonometry. What is cos 45? Punch your calculator. You get what? 0.7071. Am I right? Now if you do that, you have maximum torque multiplied by 0.2929. Am I right? Yes, I am correct. Okay, that is the work done. Because what is our maximum torque? 4 times 10 to the power of negative 3 multiplied by 0.2929. And if you press that in your calculator, you should be having this times this 0.0011716, if I'm not mistaken, joules. And if I put that to standard form, I have 1, 2, 3, so 1.1716 times 10 to the power of negative 3 joules. So this is the answer for the work done. Alright, so this is all for this. So just remember how to solve your question, write your parameters, write your equation needed, change everything to SI units, right? And then you solve. And that's all for this question. Alright, so you can pause the video, look at it again in the beginning. And let me tell you how to learn physics. It's very simple. Whenever you've learned a question or you've been taught a question, the best way to learn that question very well is after you've learned that question, you rewrite that question on paper, you pause the video or take away the textbook or whatever and try to remember what you've learned, and you solve that question again. By so doing, the question and how to solve it is being registered to your brain. It's as easy as that. That's why you need to start early and practice. You practice, you practice, you practice. Alright? So when you solve a question from a textbook, you can start with an example. You read an example, okay? You see how it's being solved. Okay, how do I get this? You learn how they got their step by step. You learn everything. When you're done and say, okay, I've learned it, you write that question from that example, close the textbook, and on your own, without picking in that textbook, you try to solve it the way it's being solved. And secondly, after you've solved it the way it's being solved, you get another paper and be like, okay, can I use another method? If possible, you can. If not possible, then you can still maintain the method you have learned from the textbook. It's as easy as that. Alright? Practice, and whenever you've learned one question, just don't resolve it just once. Even though you've resolved it and you got it, you do it again and again. At least, the minimum should be 5 times. As easy as that. Physics is not hard. Alright? You try 5 times, you solve the question, you solve the question, solve the question, go to the question 2. You ask yourself, what time do I have? Start early. When the semester begins, you start early. Every blessed day you study and you study and you study, and then you excel. Alright? You learn the theoretical aspect of physics, you learn the calculation aspect of physics. It's as easy as that. Alright? You can even join my WhatsApp channel, right? I'll post there on the comment section. You can join them. I'll be posting question. Just try it out. You try it out, and you'll be good in physics. Alright, so let's move on to the question 2 and see what the question 2 have for us. So question 2. Alright, solution. Alpha, like the video. Yeah, press subscribe. That bell sign. Press that subscribe. Press on. Don't press on. Press that subscribe. Very good. Yeah, wait. You can for solve. Share this video. Share them. Share it to the department. Share it to your friend. Maybe they learn this to share them. Yeah, share. I know. I go wait for you. I go wait for you. Yeah, share. Well, like that in first. So yeah, subscribe that in first. Yeah, share. I wait for you. Don't share them. No solve now. I mean, I don't watch video. I go like the video. Say no. Won't subscribe the video. Say no. Give person more out. No, even subscribe. No, continue to solve. Okay, for question 2 now, question 2 now is very simple. It says a positive charge Q1 is equal to 10 nanocoulomb and is at the origin, okay? And a second positive charge Q2 is equal to positive 16 nanocoulomb is on the x-axis at x equals to 4 meter. Find the net electric field at a point P on the x-axis as x equals 7 meter. You understand? First step to do is this now. Now you hear the word origin, x-axis, alright? So this is an axis form, right? So this is x-axis, or assuming an x-axis. And the question says a positive charge Q1 is at the origin, obviously, or yes, of course. The origin at 0, right? So the position of charge Q1 is 0 and is positive 10, right? Nanocoulomb. Am I right? Are you following? And a second positive charge Q2 is equal to positive 16 nanocoulomb. It's on the x-axis as x equals to 4 meter. So let's assume our 4 meter is around here. 4 meter. And positive charge, the second one is equal to what? Positive 16 nanocoulomb. Right? Okay, find the net electric field at a point P on the x-axis at x equals 7 meter. So I'll zoom here at our 7 meter, right? And the point P is over there. Now, from the former video, if you remember, an equation states that the electric field felt by a point P on an axis, alright, by a charge is given by electric field is equals to K Q over R squared multiplied by the position of where the point P is minus the position or where the charge Q is, all divided by the resultant distance between the points P and the charge Q. Now we're asked to find what's the net electric field. In this axis there are two charges, and those two charges are emitting electric field, right, on point P. So the net electric field on point P will be the sum of electric field from Q1 to P and Q2 to P. So you find electric field from Q1 to P, they add it up, the electric field from Q2 to P, and that's the net electric field. As easy as that. So for the first part, P Q1. Alright, so what this states is that would be our constant of proportionality has a value which is what? 9 times 10 to the power of 9, all multiplied by the charge Q now in consideration is Q1. In fact, yeah, they did the formula, but it's Q1 in consideration. So what is our Q1? 10 nanocoulomb. Well, nanocoulomb is not a unit for what? Charge, right? The unit for charge is coulomb. So nano is what? So this is 10. Then nano is times 10 to the power of what? Negative 9. Alright? All divided by. Now what is the distance between Q1 and point P? Q1 is 0. Now, and since this is a vectorial question, alright, so we'll make use of the components, the I, J, and K components. So for the x-axis, we use I for x-axis. For the y-axis, we use J, and then we actually don't use K, alright, just the x and y mostly. So here is I. So Q1 is on the origin, which is 0, right, and P is 7, right, and these are all I direction, right. So the distance between Q1 to P is 7 because Q1 is 0 and P is 7. So the distance is 7 and 0 is what? 7, right?
So and in meters, 7 meters, standard units, right? So that is 7 squared. Then multiply by the vector now. What is the position of P? 7. 7I. This is the vector now. This part is the vector. This is just the electric field emitted from the charge Q, right? So 7 minus what's the position of charge Q1? For Q1 now is at 0, right? So 0I divided by, now remember this R and this R are the same thing, right? Which is just over what? 7. Do you understand? Alright, so if you do the multiplication, what you get E P Q1 is equals to this and this is what? 90 over 7 squared is 49, multiplied by 7I minus 0I is 7I, right? 7I divided by 7. Okay, and if you do that, you have 1.84 times 7I divided by 7 is what? Just I, right? That is equal to what? 1.84I. So I'm done with the electric field that P is feeling from Q1. And let's go over to the electric field that P is feeling from Q2. Right, so the same thing that we did here, same thing that we do for the Q2. So that is E P Q2 equals to this same formula. So our K is 9 times 10 to the power of 9, right? This bracket times, now the charge in consideration is Q2. What is Q2? 16 nanocoulomb times 10 to the power of negative 9, right? Right. Now divide by, what's the distance between Q2 and P? Q2 is at 4 meters, right? And P is at 7. Do you understand? So from 4 to 7, the distance between Q2 and P is 7 minus 4. And 7 minus 4 is 3 meters. This is 3 squared. You get, then multiplied by the vector now. What is the vector? What's the position vector of P? 7 still, right? 7I. What about for Q? 4I. 4I all divided by what distance between Q and P? 3. Right? Right. So if I do the multiplication, this I'm doing everything at once, so I should have 16 here. 16 multiplied by 7I minus 4I is 3I over 3. This is 16 times 3I divided by 3 is what? Just I. So 16 times I is 16I. So now this is the electric field that P felt from charge Q1, and this is the electric field that P felt from what? Charge Q2, 16I. The net electric field is the sum of the electric field that P felt from charge Q1 and electric field that P felt from charge Q2. You add them up, and what will you get? Now let's solve it now. The net electric field will be E P Q1 plus E P Q2. What is the electric field that P felt from Q1? 1.84I, right? What is the electric field that P felt from Q2? 16I. And when you sum that, you have what? 17.84I Newton per coulomb. Or if you want, you can take the magnitude, or you can just leave it as 17.84 Newton per coulomb. Any of this in your exam, you might see any of this, but your test, just leave it this way. Alright, so this is the net electric field that P have felt. Net electric field. Alright, so this is simple, very very simple. So anytime you see something about a point P, electric field that a point P is getting, is receiving, you make it the vectorial part of electric field. That's easy as that. But anytime the point P is not present, you don't make use of what the vectorial part. The vectorial part is strictly meant for whenever there is a particular point, whatever p or point whatever is feeling an electric what field. That is where you make use of the vectorial part of the electric field. I'm sure you guys understand. All this thing is very, very simple. You practice, please practice. Keep on practicing. You can do this. Keep on practicing, and you will succeed. I promise you, you will succeed. It's A you're looking for, you get the A. They say it is impossible to pass in physics department. It's not true. I have passed my physics, so you will pass your physics. So let's move on to the next question and let's see what we can get from the next question. Moving on to the next question now. Question 3 says a point charge Q is equals to 4.00 times 10 to the power negative 9 coulomb is placed on the x-axis at the origin. What is the electric field produced at x equals 25.0 centimeter? X-axis. We're not making use of vector now because there's no point P filling the electric field. It's just that a charge Q is on x-axis and it's an electric charge. Alright, so now make use of the vectorial part. So the solution, so this is just the formula used for electric field when a charge is emitting what electric field, which is E equals to KQ over R squared. That is all. What is our charge? Our charge is what 4.00 and 10 to the power negative 9 coulomb, and our distance, the radius is at the x-axis now is 35.0 cm. And converting this to meter, you divide by 100, you get 0.25 meter, right? Electric field E will give us K is 9 times 10 to the power of 9 multiplied by Q is 4.00 times 10 to the power of negative 9, all divided by 0.25 all squared, right? And then to solve that, you have 36 divided by this all squared is 0.625, and therefore when you divide these two, you have something like 576 Newton per coulomb, right? And this is all for this question. As easy as that. So whenever the question is given to you, it may look like an x-axis or y-axis. As far as there is no points whatever filling the electric charge, you don't make use of the vectorial part of the electric field. It's as simple as that. So this is the answer for this question. Very short and very simple, right? Please do not forget to like and subscribe, please. So let's move on to the next question and let's see what we can do. So the next question says find the electric field at a point 20 cm from a charge of 20 microcoulomb, full stop. So that's like the first part of the question. Second one is what force will the field exert on a charge of 5 microcoulomb placed at that point? Two different questions in one question. Let's solve it. So solution, let's solve the first part now. Solution, so the first part, find the electric field. E, electric field, find it, right, at a point 20 cm. The point, that is R, equals to 20 cm, and 20 cm to meter, you divide by what? 100, that is 0.2 meters, right, from a charge 20 microcoulomb. So the charge is 20 microcoulomb. Microcoulomb is not the what SN is for what charge. That is equals to what 20. Micro is what times 10 to the power what negative 6 coulomb. You understand? Very good. So let's find electric field. So we have charge, we have radius, electric field. So we find electric field at a point from a charge. So a charge now is emitting the electric field, right? So use equation. E is equals to K Q over what's R squared, right? Now what's our K? 9 times 10 to the power of 9 multiplied by what is the charge now? 20 times 10 to the power of negative 6, all divided by, right, what is our R? 0.2 all squared. And when you point the calculator, sorry, give me time. This time this and this should be 1.8 times 10 to the power of this time this is 5, right? 5 divided by, then this all squared is 0.04, right? 0.04, and if you divide that, 4 goes in 18, everything will be what? 4.5, right? 4.5 times 10 to the power of 6 per column, right? This 2, yes, I'm correct, right? So that is that for electric field. So now the second question says, what force? What force? Force is what I have to find now. With the field exact, with that same field, this same field exact on a charge of 5 microcoulomb. So our new charge now is 5 microcoulomb. An electric field still is this one, 4.5 times 10 to the power 6 Newton per coulomb. What force? So which equation equates force and electric field? E equals to force over charge, right? So therefore force is equal to charge times electric field. So force is equal to, what is our charge? Which is 5, right? So that's going to be 22.5 Newton. And 2.5 Newton is our force. So it's quite easy, right? So remember the steps, write down the parameters, write down the equation, write the equation, impute, check everything is what in SI units, impute, you solve, and then you get your answer. So this is all for this question. In fact, this is all for the electric field itself, the whole electric field. So this is everything you learn from the part 1 of problem solving. So this one, the part 2 of problem solving. So it's all for this. Yeah, it's all you need for electric field. So just wait for the next video. Please remember to like and subscribe, share to your department, to your friend, to anybody, share, then also like and subscribe, and your comments also. I still remain Franklyn Einstein. See you in the next video.